And the second one that you really need to know is something called the relay switch. And a relay switch is something which is used to switch on a circuit which uses a very large current. So this is a relay switch. And over here where E and F are, you would have another circuit. Now, one of the things that this might be used for is the starter motor of a car, which requires a very, very large current, maybe as much as 30 amps or even more than that. And so you can see these wires are much thicker. You can't see the rest of that circuit there, it's not shown. So you don't want actually to touch something which would turn on 30 amps of current, because if there was a fault there, that could kill you. So what you do is instead you use your key in your car or some other switch to connect this circuit here. So there would be some kind of way that you would be closing a switch here, and you would close the switch at B and D here, and what would happen then is you would be turning on the electromagnet, which is this part with the coil. So we'll just write down maybe a few things here. So first of all, the electromagnet is on, switched on. What does that do? It attracts part A, so we'll say it attracts A. At the other end of A then, so as this moves down, then this is going to move up. So part P moves up because it's on a little pivot here, as you can see. And sometimes you might be asked to calculate a turning effect here using moment as force by distance. So as part P moves up, what does it do? It closes the contacts at C, closes C. And then what does that do? That switches on the circuit. And I'm just going to call it EF. So that's the way that you use a small current in the electromagnet to turn on a very large current. And once that's started, then it works on its own. It has its own battery and so on, and this relay part isn't needed anymore. So this is an example, and it just shows you a relay and two circuits. So whenever you close the switch here, you have got your electromagnet here switching on. It pulls down towards, because it's attracted, so this iron arm is attracted to the core here, pulls down this direction, and this end pushes up. Now, before it's pushed up and before this is switched on, you can see that this circuit here is complete. You can see there's a complete circuit there, and this lamp too is on. But whenever this is attracted and pulls down this direction here, I'll just put a wee arrow down, that moves up. These then are in contact. The top circuit then is closed and lamp 1 is switched on, but this contact here is broken and lamp 2 is switched off. So you might be asked to explain how something like that works. A loudspeaker as well will use an electromagnet, and the way to use an electromagnet is a loudspeaker would be connected to your alternating current supply. And when you can see there's a magnet in here, and whenever you turn on your current here, you make this part here with the coils also a magnet. So the end of the cone there becomes a magnet. So what do two magnets do to each other? They exert a force on each other. And what happens then is, because this is alternating current, the magnetic field around the coil is first of all in one direction, and then the opposite direction, one direction, and then the opposite direction, and continues as long as alternating current is working. So what happens there then is that the coil is going to be attracted to the South Pole, it's going to be repelled, attracted, repelled, attracted, repelled, as long as alternating current is working. And this makes the paper cone move in and out, and that causes vibrations in the air, which causes sound. So these are just a few wee questions here. Which material below will not stick to a magnet? So you've got steel, you know that it's magnetic. Aluminium, you know, isn't. Iron is, steel is, so the answer there is B. Which of the following below will not increase the strength of electromagnet? More coils of wire, you know, will. More current, will. An iron core will, but copper is not magnetic and will not increase the strength of the magnetic field. Now, the last part of this section is explaining why a wire which is placed in a magnetic field and it's carrying a current will experience a force. So it says a wire carrying an electric current experiences a force when placed in a magnetic field. Now you remember that your little wire, when it has got current flowing through it, moving charges, it has its own magnetic field. And you also know that whenever you have one magnetic field and another magnetic field, they interact with each other, so they attract or repel. And you don't really need to know which direction that these move. This moves, but what will happen there is that this wire will experience a force and it'll either move into the page or out of the page, in or out of the page. So it experiences a force. And the reason is because it's got a magnetic field around it. When it's placed into an external magnetic field, such as our north and south pole here, then it experiences a force. And this is the basis of the electric motor. So the electric motor. Now, an application of an electric current, a wire carrying electric current experiencing a force in a magnetic field, is that of the electric motor. And electric motors are used in everyday appliances all the time. Anything that has a part that's moving has a motor in it. So what you have here is an electric current flowing from the battery. It goes in through this side of the coil, right in through there, and then out through the other side. And this part here is free to turn, so it's allowed to turn over. So this side of the coil is connected to the positive side of the battery, and whenever it's placed into the magnetic field, it experiences a force, just like in the last picture there, or the last slide, the wire experienced a force. And that force will actually cause that side of the motor to move downwards. On the other hand, this side of the coil is connected to the negative terminal, and when it's in this field, again, it's got its own little magnetic field which interacts with the external field, and it will move upwards. So the motor will actually turn in an anti-clockwise direction. And on the end of the motor, you'll have your beaters or blade for your electric whisk or for your electric lawnmower, and that's what causes them to turn, and it continually, in this case it's anti-clockwise, continually turns in the same direction. Now, whenever this side of the coil gets over here, instead of being connected to the negative side of the battery, it will now be connected to the positive side of the battery. So instead of this side now getting over here and experiencing an upward force, it will also experience a downward force. So that means as the two sides change over, they experience first an upward, then a downward, then an upward, then a downward force. And that causes this continual turning in an anti-clockwise direction. If you change the terminals of the battery, you'd find that your motor goes the other direction. So it turns in a clockwise direction for the same reason.